This lesson is basically about carbohydrates, and it's geared towards SBI4U, or grade 12 biology. Just a reminder that you should understand the concepts of functional groups and hydrocarbons a little bit in order to understand this lesson. So carbohydrates, basically, we think of them as sugars, and when we look at the sugars, there's simple ways to remember them. So I can list a bunch of them down. So like glucose, okay, or fructose, okay, those all end in ose. So when you're looking at things that are sugar-based, quite often they end in ose. Another general term is a saccharide. So the monomer that you might talk about in a carbohydrate is a monosaccharide. Or if there are two sugars stuck together, that would be a disaccharide. And then there's the polysaccharides. So when we start talking about joining molecules together, remember that's through dehydration synthesis. And so if you put two monosaccharides together, you're going to get a disaccharide plus water because it's dehydration synthesis. And we'll talk about that on another slide. Carbohydrates, their primary functions are energy. So it's either energy storage, easily accessible energy, or immediate use of energy. In a later guide, we talk about cellular respiration, and glucose is your key starting point for that. And in photosynthesis, the product of photosynthesis, other than oxygen, is glucose. There are also some structural polysaccharides we want to talk about, and that would be chitin and cellulose. Little trivia, cellulose is the most abundant organic compound found on the earth. And later on, when we talk about nucleic acids, we will talk about a few simpler sugars that are pentose sugars, ribose and deoxyribose. If you notice that pentose is a 5-carbon sugar, whereas the hexose, like glucose or fructose and galactose, those are hexose sugars. And the common chemical formula for the hexose that we talk about is C6H12O6. And all sugars are either a ketone or a aldehyde, in that they're a carbonyl group, and there are also hydroxyl groups attached to each of those. Okay, so what we're going to talk about next is the structure, and we're going to look primarily at glucose. In my class, you will never have to draw fructose or galactose. You might have to recognize that they're sugars, but you will never have to actually draw them in that class. But glucose, yes, for sure. So when we start looking at structural details, I'm going to look at glucose as your first monosaccharide, okay? It is also a hexose sugar, which means it has 6 carbons. When glucose is sketched, most of the time we sketch it when it's in the presence of water, so it is actually a ringed structure. And so if I just want to do a quick glucose, I'm going to write the carbons in for this first one, but after that I will not be marking in carbons. And each time there are 6 carbons there, so that would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So you start counting from the oxygen, and off of each carbon is a hydroxyl group. And OH, and then there's the H's that go off of it as well. But I'm not going to sketch in the H's. They're there, okay? So a simpler ball and stick diagram that is often drawn looks like this instead. Okay, you do not need to write in all those carbons. You can just draw it as a ball and stick. That is a standard diagram. And what I've just drawn here is alpha glucose. And the difference that we're going to look at is the difference between alpha glucose and beta glucose. And the only real difference is the position of this hydroxyl group. Because in beta glucose, which I will sketch right here, I will do that in red. So beta glucose has the same hexagonal shape and you will notice the only difference being the position of that OH group. Okay? And so this right here in red is the beta glucose. And this will be apparent shortly. Alpha is usually for energy storage. So we look at energy. Usually we're talking an alpha glucose. Beta glucose is often a structural molecule. Okay? The way I like to remember these things is alpha kind of looks like a fish, right? So if you look at alpha being a little fish, and beta being half of a butterfly, because then if I put a beta backwards, I have kind of a butterfly shape, right? So if you look at the first one, alpha is below the water, because fish live in the water, and over here, beta is above the water, and butterflies swim above the water. So if you can remember that, alpha glucose goes down, down, up, down, and then every other one for beta would be up, down, up, down. And if you can remember that, hopefully you can sort of always remember the difference between alpha and beta in terms of their structure. Now that we've looked at the simple glucose monosaccharides, or the monomers, let's take a look at disaccharides. The disaccharides that we are looking at there's maltose, or malt sugar, and that's a disaccharide that's been produced by glucose dehydrated, synthesized with another glucose. We have sucrose, which is a glucose, and a fructose. And then you have lactose, which is glucose, and galactose. People always say, well, how do you remember which is which? Well, the easiest one to remember, well, other than they all have glucose as their first monomer, the second monomer will lactose and galactose. It tells you galactose. It already has lactose in it. So you know lactose is going to be glucose and galactose. Maltose, that's just malt sugar, so it's glucose and glucose. Sucrose, which is our table sugar. Sucrose being table sugar, oh, that's coming, you think of, oh, it's like sugar beets and sugar cane. Well, they're kind of like, think about it as fruit. Oh, fructose. So that's how you remember. Remember, all of the monomers are C6H12O6. So if I wrote it as this, you wouldn't be able to tell what was produced because you don't know if it's glucose, galactose, because they're isomers of each other, correct? So lactose, sucrose, and maltose all have the same chemical formula, and that would be C12H22O11. And you're going, well, wait, where's the other two H's and the one O? Oh, because you need water in there if you're going to, say, in this reaction, hydrolyze one of the disaccharides, because water is either removed when you're synthesizing or it is added if you are decomposing it or hydrolyzing. So that's the other reason there. So let's take a look at polysaccharides. Okay, those are your polymers. So your polysaccharides are your residues of glucose. We usually just deal with glucose here, and we're talking hundreds to thousands of glucose molecules in a macromolecule. Okay, so we're talking a very large, huge polymer here, okay? And your alpha-based polysaccharides are your pardon me, that's my brain, well, in your plants, you have your starches, okay? And your starches are typically amylose, which is a single-chained alpha-1,4 linked polysaccharide, and then your amylopectin, which is alpha-1,4 linked with alpha-1,6 side branches. Okay, amylose is more soluble than amylopectin. Amylopectin is not soluble, although they're both hydrophilic, so they both absorb a lot of water. And when you think about when you want to thicken things, you start adding cornstarch or pectin to things. That's where you're getting it, because it's absorbing the water because they're so hydrophilic. Okay, so you've got your starches, and those are basically plant-based. And then you have energy stored in your animals, and that's our glycogen. And in humans, for instance, we store it in our liver and our muscles. And it's very similar to amylopectin. It's alpha-1,4 with alpha-1,6 side branches. And those side branches are much more prevalent in glycogen. It happens almost every 10 glucose molecules. So the 1,6 branches are more prevalent than in amylopectin. So the glycogen is animal and mostly animals stored. Sorry about that. And then when we start looking at the beta-linked polysaccharides, we're dealing with cellulose, primarily in, again, plants. And it's beta-1,4 linked. Okay, and most of it is kind of strange because they flip the cellulose residues, the glucose residues. Flip orientation, every other one. And then the other one is, we'll just throw in, it's found in some animals and in fungi, and it's chitin, and it's again beta-1,4, but there's also amino groups on it, on the glucose. So it's a special strange one there. So let's continue with looking at the building of a polysaccharide. Let's just show that. So we're going to look at a alpha glucose. Again, remember, down, down, up, down. And we're going to mix it with another glucose, And remember when I said we did alpha 1,4 bonding, alpha 1,4 linked? We'll take a look at your carbon here. That carbon there is 4, and the carbon here is 1. So this carbon, carbon 1, is going to link with carbon 4. And when you link it, it's through dehydration synthesis. So dehydration synthesis, if you remember that, is when we take water, we dehydrate, we make water, and we join together. And so what we're going to do is we're going to take this OH and this H, and we're going to make water out of it. And what we end up getting here is a disaccharide with a glycosidic bond. Between carbons 1 and carbon 4. And I haven't filled in all the other OHs. Let me do that. And if you remember, if I took 2 glucoses and put this together, I would get a maltose and water produced. So that's how we do it. And if you want to make an amylose, you just continue to add more and more glucose residues to the maltose, and then you will have a polysaccharide built of either amylose, amylopectin, or glycogen. Now the only difference between glycogen and say amylose is that side branching, and then you just have to figure out how to put carbon 6 to carbon 1 on another one, and then it continues this 1,4 after that as a side branch. Cellulose is slightly different. I'm just going to do a quick schematic of starches. Okay, the starches look, if you look at it, where the O's represent, these O's represent starch or glucose residues, and then the little V's are your glycosidic bonds. Cellulose, when it bonds with the beta 1,4, and you have residues that flip back and forth, what happens is you end up getting, so if I was to draw a schematic just showing glucose residues again, and the glycosidic bonds for that basically alternate, and they go up and they go down. And so what happens here is you have a structural molecule and then neighboring cellulose molecules. So if I was to draw it, because it becomes a linear whereas starches will often coil on themselves. With the linear, if I look at it just as I zoom way out, what I'm going to get is the ability of cellulose to form hydrogen bonds between different lines. And that's where you get the fibrous and the structures forming, in that now you've got these thousands and thousands of glucose molecules also being able to form hydrogen bonds between the different linear structures, and then you get this fibrous structure. And that's basically what we're looking at in terms of carbohydrates. A reminder, they're primarily for energy, and some of them are structural. If it's energy-based, it's probably an alpha glucose or an alpha glucose base. And if it's structural, it's a beta structure, and those are the polysaccharides. You have monosaccharides, disaccharides, and polysaccharides. Hopefully this was helpful, and tune in next. We'll be hitting more biomolecules. Later.